let's go back for a minute to our constant speed buggy and see if we can't increase our understanding of the analysis. So what we're talking about was the constant speed buggy. So here's the flat surface, and we put the buggy on the surface. Okay, the buggy looks like this. Okay, got a little antenna here. And what we know about the buggy is the buggy goes at a constant speed. So because the buggy goes at a constant speed, we have a sense of what the position graph and the velocity graph should look like. So wherever we designate our 0 from, let's say our 0 is back here. Our buggy starts somewhere in front of the 0 and moves to the right, away from the 0 at a nice constant speed. So after some time, it has a new position. That is your initial position. That's your position after some time t. That's the change in position that we call the displacement. That's fine. We understand that. I'm feeling good about it. But what does the velocity graph look like? The velocity graph for this, well, if we remember the conceptual framework here, that to understand the velocity, you have to look at the slope of the position graph. When I look at the slope of the position graph, it's constant and positive, which must mean that my velocity is constant and positive. So that is my constant velocity value. I'm feeling pretty good about that. When we continue with the analysis a little farther, we can see some actually really interesting things happen. For example, this runs from 0 to time t. So because it runs from 0 to time t, the change in the time is actually just equal to t, because we do final minus initial. T minus 0 is just t. So in this case, the change in time is equal to the final time. So do we have an equation for the top graph? Well, the top graph is linear, so if we use y equals mx plus b, on the y-axis is the position, on the x-axis is the time, the intercept is the initial position, the position at time 0, and the slope of that graph is the velocity. So we end up with that mathematical model there. This goes along with this graph. So if you wanted to know the final position, you would need to know the speed, the time, and the initial position. No big deal. Another thing we can do here is we can analyze the slope of this graph, because that is one of our understandings, is that the slope of this graph should be our velocity. And so if we look at the slope between those 2 points, how are we going to figure out the slope? Well, it's the ratio of the vertical change to the horizontal change. What I like about this is that these two things look different, but I'm not actually sure they're different at all. Let me show you what I mean. If we take that mathematical expression and we subtract x0 from both sides, x minus x0 is equal to vt. Well, isn't that the displacement? Isn't that the change in position? And now what I notice is, according to this statement here that says that the change in time is actually the time, because we're starting from 0, if I divide, I end up with this statement right here. The velocity is the change in position divided by the time. The velocity is the change in position divided by the time. So those two statements are mathematically equivalent, and conceptually they're also the same thing, because the slope is the velocity, and in here the slope is the velocity. And that's all well and good, but what we're going to do is we're going to now consider this. How did we get from this graph to this graph? Well, we analyzed it in terms of this framework. That to go from position graph to velocity graph, we analyze the slope. I wonder if there's a way for us to analyze going the opposite direction. When we go this way, it's the slope. How do we go back? How do I take information from the velocity graph and translate it onto my position graph? That's a great question. Here's what we're looking at. I'm going to come over here to this graph. This is the same time t. That's the same time t there. And what I'm going to do is I'm going to drop down a vertical and create a shape here. This shape is a rectangle. Let me shade it. I wonder what the area of that rectangle looks like. Well, it's a rectangle, so it's base times height. So my base value is the time. My height is the velocity. So the area of this rectangle is equal to VT. And what's cool about this is that I also have this same thing over here. It's also a VT up in this corner. So it turns out so the area between your line and the horizontal axis on a velocity time graph is the displacement. It is the change in position. So when I look at this, what I'm noticing is that if you want to go from position to velocity, you analyze the slope. But if you want to go from velocity to position, you have to analyze the area.